closing talk for the day with a story that spans decades concerning finding bubbles of condensates in various settings, from a baked Alaska scenario to ground-based optical lattices, and as Eduardo said, to space, where right now our collaborators are realizing these structures aboard the International Space Station as we speak. So I'll tell you how the journey went all the way there. And this is really, I would say this is a very typical ICMT type story where people come together, ideas come together. And so really what I'd like to do is offer this as a tribute both to the ICMT and also to Tony. So, where this all began when more or less I came here as a postdoc now a little over 2 decades ago. And I came as a postdoc of Tony and Paul, who was not at Stony Brook then, but was right here, and the first director of the ICMT. And it was just so marvelous to be guided by them and mentored by them, but also to just, as is typical here, to learn so much from mentors, peers, juniors, and with the warmth that people have been talking about. And that's what really prompted me to stay on here as faculty joyfully day after day. One last piece of this whole thing is that I had just come from, I just graduated from UCSB, and with Matthew Fisher as my advisor. And Matthew, as you saw this morning, had been a student here much before, with Tony as his advisor, Eduardo as his mentor. And so really it's all in the family. And so now that makes Tony my academic granddaddy. So, so my part of the story really began around 2000 when I came here. But the story for today goes a little further back. And so where is this whole quantum bubble? Where did it really begin, this story today? And it really began with a mystery in the arena of the paired states of helium-3, which we know as a fermion. And if you look at the superfluid, there's different phases, as we saw in Vidya's talk today, the A phase, the B phase. And the mystery came about with how you can really have, when you cool the A phase into the, the temperature enough to nucleate the B phase, the problem is, because the free energies are so close and various other considerations, if you had a homogeneous scenario to account for the nucleation of these regions of helium B, if you had a homogeneous scenario, it would take about the age of the universe or longer for this kind of nucleation to happen. So how does this really come about? And so if you look at Peter Schiffer and Doug Osheroff's RMP, they tell you what happens. As a possible solution to this mystery, Leggett proposed a diabolically clever nucleation mechanism called the baked Alaska model for its topological similarity to the dessert of the same name. And it's diabolical not only because this has this Halloween-esque quality of giving you cavities and the like, but Tony actually invoked the heavens to come up with a sort of possible answer to this. And it's really quite beautiful. And the idea here is that perhaps it's possible that you have cosmic rays, coming from the skies. And if you could have a cosmic ray pass through this, then it's possible to have local heating, like a burst of energy, local heating at a point, create a blob with T greater than Tc, And then what's really beautiful is that this thing can actually expand in the shell-shaped structure. And then in the interior of the shell, the circumstances are right enough to nucleate of the helium-B phase. So absolutely beautiful picture. And in fact, Peter Schiffer, who also was here in Urbana for a while, he and Doug Ashraf actually showed through experiments that this kind of thing does indeed happen. So when I saw this, for me, it was absolutely enchanting and intriguing. And in retrospect, I realized that there were some lessons that I learned from this treatment here. One is condensate bubbles are cool, ultra cool, in fact. And then one of the things that Paul had taught me when I was their postdoc is that nothing is out of bounds when you're doing these explorations. And so here you see an instance where you have everything from the quantum to the cosmic coming together beautifully. Another thing that I learned was this whole sort of Urbana style of physics, where we really work closely, theory and experiment. They go hand in hand, something, for example, that I've been doing a lot with Dale. And there's really this remarkable way filled with camaraderie where we think, imagine, predict, come together. And so, for example, this baked Alaska scenario is a beautiful example of that. And finally, I think it's fair to say that I have learned, if you have a sweet tooth, the body will indulge in it. And not only does it give you new ideas for physics, but as Matthew told us with the Reese Buttercup scenario as a physicist, you can always optimize the best dessert. Okay, so one more thing that one last thing that I want to say before we go in, before I tell you how this inspired some of our adventures, is that of course all this was in the backdrop of the bigger mystery. And the bigger mystery was, I mean, what are these paired states of superfluid helium-3? And of course, as we well know, it was Tony that masterfully answered this. And I actually remember I had the privilege of just coming here, and a year later, that's when he won the Nobel Prize. And afterwards, I was at Cornell, my undergrad alma mater, and there David Lee was so excited, and he said, Tony found the Rosetta Stone for this. And of course, you know, he had these masterful answers for what the possible phases of superfluid helium could be. So now I can't at all tell you about what lessons can be learned here. I would need many, many lifetimes here. But the person who is here, the person uniquely able to answer that question is right here. How do you solve this mystery? How this? How that? How to be an adventurous, deeply thoughtful, creative, gentle knight. So, Tony. And so with that, let me embark on the adventures that we went on with condensate bubbles. And let me just say, so this is this part, the baked Alaska, and now I will tell you about what followed subsequently here. So for us, there's two differences compared to the condensate bubbles that you heard about now. One is where everything that I'll be telling you about is looking at bosons. So these are condensed bosons. And the other thing is that when you look at the bubble, it's the condensate itself that forms a shell-shaped structure. So now let me go on to the first instance, which is the optical lattice. And so how can these kind of structures naturally come about? Where are the different settings in which you find these kind of shell-shaped structures? One is optical lattices. Another is actually when you look at ultra-cold gases, AMO type physics, there's various places where you actually find these kind of condensate bubbles. One is in the optical lattice. I will tell you about how that comes about. Another could be mixtures of gases like fermions and bosons, perhaps free space, and that's something I'll tell you about at the end of this. And finally, going back to the quantum and cosmic theme, In fact, things that Gordon, for example, studies is if you look inside the, if you look at the structure of neutron stars, these two have shell-shaped structures. And despite the temperature being really high, compared to the density of the neutron star, it's low enough that you can have shells of condensates. So these are the various arenas. And in the next 15 minutes, I guess, that I have, I will focus on looking at the optical lattice and free space. Okay, so here, if you look at the optical lattice, what is it? This is the kind of thing that, for example, Brian DeMarco here does in his lab, Jake Covey as well. And the idea here is by interfering laser beams, you can create an optical lattice, and then you can trap bosons or fermions or the like. And so now the Bose-Hubbard description is as fine a description as any to look at what these lattice bosons do. And so you really have bosons hopping on a lattice, interacting, and in general, you have some kind of trapping potential. And so if you look at the homogeneous Bose-Hubbard, as we well know, there are different states of matter that can be there depending on the chemical potential and the hopping. You could have Mott insulating phases with different occupation number, or you could have superfluids, or superfluid. And so these are the typical phases that one might expect. Okay, and then if you look at, for example, characteristic scales in these optical lattice systems, you are looking at temperatures of about nanokelvin or the like for realizing these kind of phases. So now you can say, what happens if I have such a lattice and it's in the presence of this kind of trapping potential as is typical? And so one thing in a local density approximation, for example, if you had very, very low hopping, you can kind of think of the center of the trap as having this sort of being able to trap more particles. So you're somewhere up here. And then as you go out to the sides, what you're doing is you're coming down this line along the phase diagram. And so what that's telling you is that it's possible to have shell-shaped structures where you have concentric Mott insulating phases. Okay, and so then what happens, and this is something that was predicted, and it was actually, for example, you can do spectroscopy and identify these different Mott layers. Now you can ask what happens when you put on a little bit of tunneling. And if you go through the same kind of argument, you see that at the interface, when these Mott phases come together, that's where you can have the most number fluctuation. And so it's possible to actually develop a layer of superfluidity. And this is the kind of structure that you might have. So you have these concentric shells of Mott, and now in between, you can have these superfluid shells. Okay, and it's called the wedding cake, just because if you look at the density profile, it looks like this very festive wedding cake. There's a lot of dessert themes in here. Okay, so so now, and just to tell you, these were the kinds of things, structures that we got interested in. This was about 2003, 2004, thereabouts. And just to tell you who the we refers to, Brian DeMarco had just come here as a new faculty member. And Courtney Leonard is my buddy from grad school. We both graduated, both of us had Matthew as our advisor, graduated the same year. Tsu-Che Wei was a student of Paul Goldbart at the time, and Quay was my first student. And of course, they're all off doing other wonderful things now. So we started exploring these shell-shaped structures and started asking, for example, how do they form? What are spectroscopic measures? And for example, another characteristic signature, are there any sort of collective modes, for example, that one can explore in these instances? And to answer that, just to give you a little taste of the kinds of things we did, for example, if you were to ask about a shell that's between two of these Mott states, just to give you a flavor for the kind of theory we did, you can, for example, go into a pseudo spin description where some mod n may be a spin pointing up, n minus 1 may be spin pointing down, thereabouts. So we came with this formulation to describe these shell-shaped layers. And this was really done by Roman Barenkov, who was my first postdoc. And we were able to predict, for example, what the collective mode structure will be. And you can see that these things are different from filled shells, which are something that's typically studied in cold atomic systems, where, for example, you can load up, just without the lattice, you can load up one of these traps and look at the collective mode structure, and you can say things about the shape of the condensate, for example. So in this case, we were able to show that if you had a region, if you had a shell, as opposed to it being filled, there's various differences when you look at the angular modes, the radial modes, and things like that. Okay, so these were things that we were looking at in this Mott superfluid sort of system. But then after a while, we said, hey, why not just theoretically look at the system in isolation? Why not look at the shells in isolation? If there was any way to trap them in sort of free space, what would their properties be? And so we looked at various properties. For example, if you had a trapping potential and you let go of the trap, typically these are called time of flight experiments, and you can see the way the condensate expands, or what the ultra-cold gas expands, and you can say various things about the system. And we said, why not do the same thing, but with these shell-shaped structures? And so we found that there were indeed differences. So for example, if you let a shell go and it were hollow inside, a filled sphere would actually have everything expand out. The group velocity is always going out. On the other hand, with these shell-shaped structures, the outside would be going outward, the inside would be going inward, you'd have mass accumulation. And so there were all these kind of features that we thought were cute, and we said, okay, we'll study this. But there was only one problem. Experimentally, the problem is Earth's gravity. It turns out that you can't really create these things in free space because Earth's gravity sort of pulls it down and opens it up into a bowl shape or a contact lens shape. And so we said, okay, fine. We're theorists, we like doing this anyway, but this kind of thing is probably never going to be realized. Okay, so there was a hiatus, and then maybe about 6 or 8 years ago, Nathan Lundblad, who's on faculty at Bates College, luckily everybody that he knows is fine right now with the things happening there. And so Nathan Lundblad contacted us and said, hey, are you interested in your superfluid shells? And we said, yes, we're interested, but we didn't think any experimentalist would be because of Earth's gravity. And he said, I know, that's why I'm taking it up to space. And so that's when, and it was really wonderful because NASA had this, oh, it says not hearing any, anyway, okay, sorry, I just got a message that things cannot be heard. Anyway, okay. So, so what happened was that NASA was taking this cold atomic lab aboard the International Space Station, and it was really exciting for us that Nathan actually was going to have his experiment of creating these condensate bubbles, if you will, aboard the International Space Station. And thus began our collaboration. This is in 2000, well, this was just before the pandemic hit when I visited the Jet Propulsion Lab, where they have land-based controls of this cold atomic lab that's up there in space. This is astronaut Christina Koch, and she had just put some new hardware upgrade on the space station. It was all very intensely exciting. The Mars rover was getting ready, and I even got to hear the astronauts from above giving their daily updates in Japanese, Russian, English, everything. Very exciting. Okay, And so after that, we've been collaborating with Nathan's group, and there's just been this sort of real excitement here. And so what are the kinds of things they're doing up there in the International Space Station? How are they realizing these shells? And what kind of theory are we doing? And this is what I have about 10 minutes left, or not 10, 3 minutes left. Perfect. Okay, so then I know how to paste this. So what they do up there is they use something called a bubble trap. And this is just the form of the bubble where you can change different parameters, and you can either have a filled sphere or a hollowed out something that sort of can take on all kinds of different shapes. This part of the work, it's being, so the experiments are being done by Nathan, and Dave Aveline is his collaborator at JPL. And then along with Courtney and Quay, I had Carmela Padovich join. She was a student, and now she works for New Scientist. And Brandon is my current student who's actually working with NASA on this. And so we got very excited and started looking at all kinds of things. This is the actual proposal for the chip that has been realized up there. We looked at things like collective modes, for example, and we showed that there were signatures of hollowing out. Exactly when the center starts to hollow out, there's some kind of characteristic signature there, both with the radial modes and with the surface modes, because there is really a physical topological transition when you go from a filled system to a hollowed system, and these collective modes can pick those up. We also looked at things like vortices, because when you have this kind of hollow system and you say, if I were to thread a vortex through, what would it look like? This is very similar to, say, this is just fluid dynamics on some kind of closed surface. And mathematically, the flow tells you that if you have a vortex on this side, you'll also have an anti-vortex on the other side, and all kinds of things. So we started playing with these kinds of things. And these are all things that they are gearing up to look at in the coming years, which is very exciting. What they did look at, though, is they had this bubble trap, and they were able to sort of start off with this filled sphere and blow it up to very, very large sizes. And so if you look at this, this is the actual data. It's not very symmetric, but it is a closed surface. It goes up to about millimeters, which is actually really impressive. These are some of the largest ultra cold gases that are out there. The only thing is, when we actually did the sort of thermometry, so to speak, there's two competing things going on. When you make the system larger and larger, there's adiabatic cooling that goes on, so the system cools down. However, because it's also becoming less and less dense, TC goes down as well. And so unfortunately, in these largest sized bubbles, there still isn't a condensate, and that's something that they're trying to achieve. So this is just giving you a taste of where we're at. We just heard a few months ago from NASA that they're willing to support this for another 5 years. And we're really excited because there's lots of fun to be had. There can even be cosmological models of sort of the expanding universe, Kibble-Zurich physics, all kinds of things. And we're gearing up to explore that. And some of these modes some of these predictions on collective modes, it's something that they'll be looking at soon. So that brings me to the close of my story. And now if we were to, and just to come back full circle and tell you that this is just one of many examples of the kinds of explorations. And it's been wonderful to really be part of, this is our community. And every day, even after 20 years, it's something that I seek such joy in. And so let me just show you, this is my last slide here, to show you, actually, this was life before the pandemic. And now you've all come back here. We're all so thrilled to see all the life and every vibrancy that you're all bringing. And this is typically what goes on. the junior researchers, postdocs, and students, they're really the lifeblood of this place. You can see theorists and experimentalists somehow conspiring away at something. And then we have two of our beloved people writing something on the board. I don't know what that is. Maybe you do, but yes, it's, yeah. And then we've talked about the academic family, and it just so happened that the last time Matthew was visiting, my student Preeti was there, and so now you see 4 generations of advisor and student. And so this is just one academic family, but there are many, many, many ones that have come about, you know, over the course of time for all of us here, and it's wonderful. And the last thing to say is that a very, very important component, I talked about the Rosetta Stone and all that, but for it to come out into the world, there has to be a transcription from these handwritten scriptures to actually typed notes. And so one thing, that's only one, we've talked about these notes that have come out. That's only one component of the many, many, many things that happen thanks to some very important people, and they are our administrative staff, and they are part of this family. So I just want to really give a shout out to them. And so this here is our ICMT tomorrow to be named AJL ICMT. And so with that, let me just go back to my story here.
For a few questions. No cooking questions?
Oh, there's a question.
What sorts of things can be done in the
On the space station?
space?
Yeah, so there's actually 5 experiments. Some of them have to do with interferometry. Some of them have to do with these Efimov states. Others have to do with multiple species of gases. This particular one is designed to look at these condensate shells.
Instructions that an astronaut there.
Oh yeah. No. This is very. It's not. It's like literally $1 million question. That's the amazing thing. It's all land-based. The controls are all land-based. What the astronauts do, and that's something pretty amazing, just to put in the upgrade. It's not just you stick a box in there. So what they do is each time there's some new thing, they actually put that on. But then once that's installed, everything is land-based. So these 5 experiments, the main PIs of these, they kind of rotate off what the instructions are from land.
Another question? No, let's thank Smitha again.